Here we continue with the branch proof of instructions. We have already seen unconditional jump, various 8 conditional jumps, unconditional call, and the various 8 conditional calls. Now here comes return instruction. This will be the instruction given at the end of a subprogram that is being called using the call instruction. After execution of the subprogram, the control must be transferred to the main program. To do this, or to cope with this act of returning back to the main program from a subprogram that is being called using the call instruction, this instruction return will be used. Suppose we have a main program written from A500 onwards. So in A500 we have the first instruction, and at the address say A505 we have written the instruction call. The format of call is followed by the address. Let the call location be 8500, then in the address A506 I will have list significant 8 bits of the address that is to be called, which happens to be 8500. Then the least significant byte of this address is 00, and in 07 the most significant byte of the address will be written. So this instructions call written from A505 and ending at A507 asks the microprocessor to call a subprogram written that is being already fed to the microprocessor from the address 8500 onwards. So from 8500 onwards I have a program or a subprogram being written which needed to be executed as a part of execution of the main program written from the memory location with address 8500 onwards. So upon executing this main program, once this address A505 is reached, the opcode corresponding to call will be fetched. Upon decoding it, the processor will understand that this asks the processor to call a subprogram written from a specific location onwards. Address of this location is available in the next 2 consecutive memory locations of the main program. Then the least significant 8 bit of the address will be fetched into the interior of the processor, then the most significant 8 bit of the address. Thus this address A500 is generated. Now this needed to be loaded to the program counter register of the processor, and the program counter will have now a content that happens to be the address of the next memory location that is to be executed, which happens to be A508. So before going to load this address A500 to the program counter, this address that contains the next instruction of the main program that is to be executed needed to be saved to a reserved location. You already know that this reserved location happens to be the stack pointer register. Happens to be the stack register array. So you have the stack array here. Let the maximum field location in stack has an address 2998. So the stack top will be 2998, which happens to be the content of the special purpose 16-bit stack pointer register. So stack pointer register will now have a content 2998. Now A508 needed to be saved to the memory locations with address or stack location with address 2997 and 2996. This will be the activity being performed upon execution of this call instruction. As a consequence of this, 08 will be saved to 2996 and A5 will be saved to 2997. And further, the stack pointer will be decremented by 2 in order that it will be now representing the new stack top that happens to be 2996. So stack pointer is modified as 2996. Now this address 8500 will be loaded to the program counter. So 8500 will be loaded to the program counter. Then of course the program being written from 8500 will be started executing. The first instruction written at 8500 will be fetched by the processor, decoded and executed. Then the program counter will be incremented by 1 to make the new address 8501. The instruction written in this location 8501 will be fetched, decoded and executed. And in the end, suppose at 8508 the last instruction is being written, that is also fetched, decoded and executed. Now the program must be returned to the main program. Then I will have an instruction at 8509 asking the processor to return to the main program. That instruction is return RET. Once this is decoded, the processor will identify that this asks the processor to return to the main program. Then it will have to replace the present address 8509 at the program counter to the address that is being saved to the stack memory locations, that happens to be say A508. For that, it will be bringing the present content of stack pointer memory location or stack top memory location, that happens to be 2996, to the least significant part of the program counter, that happens to be say 08. And the content of stack pointer plus 1 memory location, stack pointer content is now 2996. Stack pointer plus 1 location is now 2997. Content of this memory location is A5. That will be taken back to the program counter. Then 2996 and 2997 are empty. Stack pointer needed to be initialized by means of this new stack top, that is the address of the maximum filled stack location, which happens to be 2998. Then stack pointer will be incremented by 1. So this will be the activity being performed upon execution of this instruction return. So what happened in return is that content of the memory location whose address is there in the stack pointer, content of stack pointer, that is stack top, and content of that stack top or that stack memory location, that will be taken to the least significant part of the program counter register, that now happens to be 2996. To this location we have already saved the least significant 8 bits of the address 08. And the content of the memory location whose address is the stack pointer content plus 1, that happens to be 2997, which contain the most significant 8 bit of the address that is being injected to or pushed into the stack memory location, which will be taken back to the program counter, most significant 8 bits of the program counter. Then the new stack pointer content must be earlier stack pointer content 2996 plus 2, because that happens to be the maximum filled stack location as of now. Then the stack pointer will be incremented by 2. So this will be the activity that will be performed by the processor upon execution of this return instruction. This requires 3 machine cycles, 1 opcode fetch, of course, that will be at an expenditure of 4 consecutive T state, 1 memory read machine cycle to read this stack pointer memory location and taking the content to the interior of the processor at the least significant part of the program counter register. Another memory read to read the next stack memory location and taking the content to the most significant part of the program counter, which is also within the interior of the processor. And the incrementation of the stack pointer content by 2 will be done without any time delay. So machine cycle will be opcode fetch for fetching return opcode, to memory read operations for reading the stack memory location, 2 consecutive stack memory locations. So overall the time requirement will be opcode fetch 4 T state plus memory read 3 T state plus again 1 memory read 3 T state, making a total of 10 T states. Now conditional return. This is exactly like return operation, however execution will be subjected to the satisfaction of the condition depending upon the status of a possible status register. 4 out of the status registers will be used for this out of the total 5 different registered status flags. The one exempted happens to be the auxiliary carry. Return if there is a carry, return if there is no carry, return if the result is 0, return if the result is non-zero, return if the result is positive, return if the result is minus, return if the parity is even, return if the parity is odd. So the satisfaction of this condition is required for the execution of any one among these 8 different instructions. If the condition is satisfied, then it will be executed. However, if the condition is not satisfied, then such an instruction will not be executed. So upon fetching the opcode of this instruction, the processor will check whether the condition is satisfied or not. In order to check whether this condition is satisfied or not, it will be spending an additional of 2 consecutive T states. So in order to fetch the instruction, we know that it will be spending 4 consecutive T state. Immediately after fetching and decoding the instruction in the 4th T state, it will identify that it's a conditional return instruction. So I'll have to check whether this condition is satisfied or not. Then this will be checking the relevant status flag, content of the relevant status flag, and this consume a total of 2 consecutive T states. So the opcode fetch part of this instruction requires 6 consecutive T states. At the end of the 6th T state, it will make its decision that whether this condition is satisfied or not, then it will have to move like that. If the condition is satisfied, then it will be saving the content of the stack pointer memory location to the PC lower, stack pointer plus 1 memory location to PC higher, and the stack pointer will be incremented by 2. That require 2 memory read operations, and the overall machine cycles will be 3. And the corresponding T states will be 6 T state for opcode fetching and decoding, and 6 more T states for 2 memory read machine cycles, making overall time duration as say 12. If the condition is not satisfied, these memory read operations will not be performed and the instruction will be finished by means of 6 consecutive T states. Now another one in this branch category, that is restart n. Restart n, where n can have a value from 0 to 7. That means there are a total of 8 different restart instructions. In restart instruction, what is being done is that the program counter will be loaded with a default memory address that is being known to the microprocessor by default. So what happened in this case is that the program counter